We've heard a little bit about transmission spectra, and today we're going to hear a lot more about transmission spectra. So I'm going to get us started by talking about how stellar activity impacts transmission spectra and what we're doing about it. And a lot of the talks that we're going to have today are motivated by this new shiny toy we have in space that is giving us, among many other things, exoplanet transits with phenomenal precision. I don't feel like we've been just bludgeoned with enough light curves yet, but just like, look at that. It's incredible. And what we can do when we have that kind of precision is we can measure the size of the planet as a function of wavelength and look for opacity coming from the planet's atmosphere. We can build up an understanding of the size of the planet like SAFAR has done for WAS39b here to reveal absorption from molecules, atoms, clouds, hazes. And with the precision and the wavelength coverage we have from JWST, now we can say really interesting things like, we can answer questions like, what is the metallicity of this planet? What is its C/O ratio? What does that tell us about where it formed and how it got to its current position? It's an amazing time to be studying transiting exoplanets. We can even push this to the limit, theoretically, and look for signs of life on exoplanets. We have the facility performing as expected. We have the targets, temperate, nearby terrestrial exoplanets, and we know what signatures we should be looking for. The problem is that the planet is not the only interesting astrophysical object in this equation. Stars are chaotic, energetic environments, as Jim Davenport was telling us yesterday, and they produce interesting signals as well. The stellar spottedness, so spots and faculae on a star, impact transit depths whether they're in our transit chord or not. So they do so through this thing we call the transit light source effect. It's been known for a couple of decades, but we slapped a name on it in 2018, and it stuck. It boils down to the fact that we have to assume the light source that's illuminating our exoplanet atmosphere. So in the case of exoplanet transits, we assume the integrated disk spectrum before and after the transit is what's illuminating the atmosphere. That's the spectrum we have access to. But what's actually illuminating the atmosphere comes from a spatially resolved region on the star, not just the transit chord, but roughly coincident with the transit chord. So any difference between that full disk spectrum, the assumed light source, and the actual light source ends up being imprinted on our transit depth measurements. And for some stars, the signals can mimic or mask those coming from the exoplanet atmosphere. So at the end of the day, transit depths are actually the combination of two signals, the wavelength-dependent opacity of the planet's atmosphere and the wavelength-dependent heterogeneity signal from the star. This effect is largest for K and M dwarf stars, and that's because they have significant molecular opacity that differs between their spots and photosphere. On K dwarfs, we have TiO absorption in the spots, which can be imprinted on transmission spectra. And for M dwarfs, we actually have variable water absorption between the spots and the photosphere. And that can imprint signals on the transmission spectra. These plots have some funky y-axes. So here's where a 100 parts per million feature from an exoplanet atmosphere would lie. It's really like a booming signal from an exoplanet. And what you can see is that in these stars, they are problematic because they can imprint molecular features on transit depths that are comparable to those coming from the planet's atmosphere. These are predictions for typically active K and M stars. If we have even more active stars, the signals can be much larger, order of magnitude larger than the ones coming from the planet. So the prediction from that work was that when we get the precise measurements from JWST, the signals we're going to see first are coming from the stars. And unfortunately, that's what's happening now. Stellar activity in this sense is the bottleneck for transit observations of small exoplanets. Here's one example from Sarah Moran's work in 2023. They see this water absorption feature in the transmission spectrum of this rocky exoplanet. And the bottom line that's summed up by this press release is that Webb finds water vapor, but from a rocky planet or its star. We're going to have lots of talks, including some that have already happened and some we're going to see today, and some posters that are all about this stellar spectral imprints on transmission spectra. Contamination if you come from that side of the aisle. And you know, this can get kind of like heavy, like it sort of feels like a downer. So I asked ChatGPT to write us some jokes to keep us cheered up as we're doing this. And so ChatGPT says that JWST is revealing incredible details about exoplanet atmospheres or stellar atmospheres. We're still deciding. So this is the situation we're in. We have this goal of a 10 parts per million transmission spectrum of a rocky exoplanet. And the reality is when we point at our best targets like TRAPPIST-1b, we see signals on the orders of 100 to 1,000 ppm coming from the star. To illustrate that, here is Olivia Lim's work from a year and a half ago, where she got back-to-back transits of TRAPPIST-1b. And what you can see in the back-to-back observations is we get a totally different spectral slope in the transmission spectrum, and we have a 400 parts per million offset between the data. So these are the kind of signals that we have to contend with. I don't need to tell this crowd that the best studied exoplanets have the best studied stars, or they must have them. Or as ChatGPT would put it, the goal is 10 ppm precision. The reality is not that. So with the time that I have today, I want to tell you about what we are doing to tackle stellar contamination or stellar activity in the current context. I'm going to argue that we're not limited by the data we have, we're limited by the models we have of stars. And then with the second half of this talk, I want to tell you about how we can get around these model limitations and try to study rocky exoplanet atmospheres today through some empirical techniques. So our model-limited regime. I'm going to focus in this talk on analyses of the out-of-transit stellar spectrum that we get from HST and JWST. The reason why is whenever we do a transit observation, we usually spend as much or more time staring at the star than we do at the planet, but we're not really utilizing that data, or we haven't historically been utilizing it. What we do is we just normalize the brightness of the transit to this out-of-transit flux, which is great. If the star is just a limb-darkened disk with nothing else going on, it works perfectly. But we know stars are never like that. They always have something interesting to say. And so this is where we end up with that transit light source effect. But if we actually study the out-of-transit stellar spectrum and try to model it, can we constrain the properties of spots and faculae, their covering fractions, their temperatures, in these data sets that we're naturally going to get from JWST and HST? We can also study transit, we can study the star with the in-transit data through retrieval analyses. I'm not going to talk about those because we're going to have some excellent talks coming up that will cover retrievals of the in-transit spectra. I'm also going to focus very much on the TRAPPIST-1 system. I've heard there are other stars. I haven't looked into this yet, but for today, let's just pretend, let's just be satisfied with this amazing star, right? It's the best one. Models, so what we do when we study HST spectra of TRAPPIST-1 and do this technique of trying to fit the out-of-transit stellar spectrum to our existing stellar models is we find that our models don't uniquely identify the distinct spectral components that might be present. This has been done a number of times by people in this room, but most recently with the HST data, this was done by a study led by Leonel Garcia there, where we studied the HST spectrum in black there, along with the photometric brightness of the star, and tried to fit Phoenix or BT settle models, we tried both grids, with 1 component, 2 components, or 3 spectral components to the flux we're getting from the star. And what we find is that across the board, all of these models still have relatively high residuals relative to the data precision. In other words, we're seeing equally poor fits. What that means then is when we're trying to derive a correction for the transmission feature of the star, is that when we use this out-of-transit spectra, we can derive constraints on what the properties of the spots must be, what their temperatures and covering fractions must be under these different scenarios. But if we can't distinguish between the scenarios, we end up with an ensemble of corrections that are all equally valid. And so when we apply all of these corrections to the transmission spectrum, we end up in a spread in the data that's 5 times larger than the data uncertainty. So now we're no longer working in the photon-limited regime. Our inference of the planet's atmosphere is limited by our understanding of what's going on the star. Unfortunately, this case persists when we turn to JWST observations of TRAPPIST-1, because the data is even more precise, but the models are still at the same level of fidelity with respect to reality. So this has been done by a number of groups. We saw some work yesterday on this as well. But in this study from Fatima Davoudi, we looked at the nearest SOS and the nearest spec prism spectra of TRAPPIST-1. We fit models with 1, 2, or 3 spectral components to the star, and we find the same answer here, that in the Bayesian evidence sense, the models with more components aren't are statistically favored, they all give equally poor fits to the data, and so we can't really say whether we're constraining the spot properties on TRAPPIST-1. We know it's spotted, we see the rotational variability, but because of these model limitations, we can't turn to the JWST spectra and say, aha, it's got this level of covering fraction or this amount of spot at that time. Or as Chat puts it, it's a great system for testing atmospheric models, mostly because none of them work on it. Okay, yeah, there are other stars in TRAPPIST-1, I know that. And this model is not, this issue isn't just specific to TRAPPIST-1. This is something that crops up anytime we try to model precise JWST spectra of late type stars with the models that we have today. So I just told you earlier about GJ 486, which is an early M star, much more sun-like. They see a water absorption feature in the transmission spectrum. And they looked in the study by Sarah Moran at the out-of-transit stellar spectrum to see if they can constrain the spottedness of the star and answer the question, is that water absorption feature coming from the planet or from the star? And the conclusion of this study, when they test models with 1, 2, or 3 spectral components, is that they all give the statistically equal fits to the data. They're not able to say how spotted the star is by looking at the spectrum from JWST. So that begs the question, are we just like barking up the wrong tree here? Can we just, is there something wrong with our technique that it's not allowing us to extract spot covering fractions? Are we doing something wrong? Well, there's multiple groups doing this, so maybe all of us are doing something wrong. Another way to put this is, can we actually identify the right model fidelity, the right model complexity if we have sufficient model fidelity? The answer is yes. I don't have time to prove that to you, but just take me at my word. Julian DeWitt and I looked at a paper last year where we modeled and retrieved a bunch of different stellar spectra as observed from JWST, and we tested out this framework that we're using on all these stars here. And what we find is that the framework is fine. The framework works. We're able to constrain spot temperatures and covering fractions in our synthetic models when we use the same model grid to simulate and retrieve the data. But if we simulate the data with one grid and retrieve with another state-of-the-art grid, then we run into this limitation where we don't get a unique solution. And so what that's telling us is that the differences between the state-of-the-art models, if we use them as a proxy for the difference between our models and the reality, that's the fidelity issue that's providing this limitation in our retrievals. So how do we improve the fidelity of our stellar models? How do we get to the point where we can do analyses of stellar spectra and tell us how spotted they are? I want to highlight a couple recent results and from various groups, but essentially the answer I would say when we're talking about spots and faculae, active regions, these are inherently 3D objects, and we need to move from 1D models to 3D models of them in order to get better model fidelity. So this is kind of work that's come out of Sasha Shapiro's group, in this paper led by Smitha. They looked at 3D MHD models with the MIRAM code of spots on a G dwarf, a K dwarf, and an M dwarf. And they asked the question, if we extract spectra from these MIRAM simulations of the entire spot, also just the penumbra of the spot, the umbra of the spot, and then we compare our 3D MHD spectra to the 1D approximations that everybody is using, are the 1D approximations suitable for modeling these features at a level of precision that they're not going to interact with our transmission spectra? And for G dwarfs, their answer was, yeah, actually the 1D spectra are pretty good. You can approximate the spectrum of a spot on a G dwarf just using a Phoenix model or MPS Atlas model of a spot of a star of a cooler temperature. For K dwarfs, you're kind of pushing the limits there. There start to be some significant features that what's being plotted here is the difference between the 1D and the 3D models at different viewing angles on a normalized axis. And what they say is that there are some significant differences between the 1D and 3D models. And for M dwarfs, they say stay far away from 1D models. If you're trying to model a spot on an M dwarf, you're really not capturing the spectrum of the spot at all. What we're seeing in the 3D models does not reflect just like a 1D Phoenix model of a cooler temperature. Veronica Witzke looked at this in the case of faculae contrasts, asked the same question. Can we model faculae on stars as just like a stellar spectrum of a hotter star? And so they looked at faculae on a G2 star as a function of different viewing angles and different magnetic field strengths. And what's being plotted here again is the 1D models from Phoenix and MPS Atlas versus their 3D spectra contrasts. And what they find is that across the board, they see some very stark differences between the faculae from the 1D models and 3D models. And very interestingly, there's some behavior that's not captured at all by the 1D models. They find even on the sun, faculae at certain viewing angles are dimmer than the photosphere and brighter than the photosphere at different wavelengths. And that kind of wacky spectrum is not captured at all with our approximation of saying, oh, the faculae on this star is, it's just like the spectrum of a hotter star. So we saw earlier from Sarah Seeger, this issue gets even more prominent when they push down to M2 or M4 stars. So the answer here is that when we are simulating faculae, we really should stay away from these 1D models. So the main points for this first half of the talk is that we're in this data-rich but model-limited regime when we're studying exoplanet transits from space. We can make a good correction for stellar activity, provided that our models for spots and faculae are up to the task. Currently, our 1D models that we use widely in the community work pretty well for G-dwarf spots, maybe okay for a K-dwarf spot, but probably stay away from them if you're trying to model an M-dwarf spot. And if you're concerned about faculae on your star, the 1D approximations that we've been using really don't capture the behavior of facular spectra. We should turn to the outputs of these 3D MHD models as they're becoming available to model that. Or as Chat puts it, if we want to characterize exoplanets, we need better stellar models. Should be simple. It'll be Chat's job in a couple of years, right? Okay, so the second half of this talk, I want to talk about how we can get around this model limitation. Model development takes time. People are working on it. But we want to study those planets now. So how can we study the most exciting small terrestrial exoplanets without waiting for a stellar model development? That's the idea behind this roadmap that was put out by the TRAPPIST-1 JWST Community Initiative last year. And the idea for this review was to identify the steps that we need to take in order to characterize an exoplanet with JWST in a logical way, and how we can do that rapidly and efficiently. So that doesn't mean getting all of the time that ATAC will give us on a target. It means how can we best use this facility to get to the point where we can say, all right, we've learned what we're going to learn on this planet with JWST. Any future insights are going to wait for a future facility. So I'll briefly run through this. The first step, of course, if you have a hot rocky exoplanet, is to do emission studies. Because as Laura Kreiberg showed, and others since then, that you can use the eclipse depth of a planet and the phase curve, if you have it, to rule out atmospheres on a planet, on a hot rocky exoplanet. If you have a very large eclipse depth and a symmetric phase curve, you can be fairly confident that this rock does not have an atmosphere. That's the motivation behind the Rocky Worlds DDT that is now using 500 hours to explore the cosmic shoreline among this population of hot rocky exoplanets. So if you see a hot rocky exoplanet and you get an emission spectrum that says there's no atmosphere, then you're done with the roadmap. We've learned what we're going to learn, and we can move on. If you do see an atmosphere, or if you have a more temperate terrestrial exoplanet, you have to go through transmission spectroscopy to study its atmosphere. And there we run into the star again. We need to know the star better in order to do transit observations. But I'm going to focus on two aspects that are a little bit of a shortcut here in this road path, and that's empirical constraints on the star's heterogeneities. The first technique I want to tell you about is a spectroscopic phase curve of the star. We're not talking about getting a rotational phase curve of the planet. We want to get a phase curve of the star as it rotates. And the idea behind this is that if we can get enough data on a star as it rotates, we can build up a library of spectra that will allow us, through some principal component analysis, to identify the unique spectral contributions on the star. And then once we have that library of unique spectral contributions, we can recreate the stellar spectrum at some later date using that database and derive a correction for the TLS effect. So postdoc at MIT, David Berardo, took a look at this technique and its potential limitations with some simulations of JWST spectra. And he found that for stars of different rotation periods, there's sort of a bottom line, which is that if you want to reduce the level of noise on your reconstructed stellar spectrum to below the noise on the transit observations, you need about 20 hours of data on a star. Ideally, you could do this over a single rotation, so you get the star hasn't evolved very much, but you can identify those unique components that you can use in the future as the star evolves to reconstruct the spectrum. We're hoping to do this with a single rotation of a star, but right now we're also exploring the archival data from HST or from JWST on TRAPPIST-1 to see if we can do this same sort of technique on TRAPPIST-1 with what's already in the archive. What if you don't have 20 hours? Is there anything else you can do? The last technique I want to share with you is the potential of double transits to provide empirical corrections for the transit light source effect. We're going to learn a lot more about this from Natalie Allen shortly, so I won't step on her toes too much. But the idea is that if you have an inner planet that you think has lost its atmosphere and an outer planet that you think still has an atmosphere, and they share roughly the same transit chord, transits near in time should have the same signal coming from the star, the same transit light source signal. So you can use transits of an inner and outer planet near in time to isolate that signal, and then you can correct here's your control sample, here's your experiment sample. You can correct the experiment for the control. So Natalie's going to show you the results of her ongoing JWST program, which is collecting 15 transits of B and E to study the atmosphere of E. I want to just give you one other example from the recent literature, which provides a test case for this technique. Because last July, 2 bare rocks transited TRAPPIST-1 at the same time, B and C. And so in this paper led by Alexander Rathke, we're just wondering, does this technique work? We have 2 bare rocks. Can we divide their spectra and get a flat line? And so this is what the transmission spectra look like. I'll walk you through this plot one at a time. So starting in the upper left, we have the transmission spectra of TRAPPIST-1B and C. And you can see where we have sufficient signal to noise that there are spectroscopic features in the transit spectra that look the same between the 2 planets. If we bin these data points at the short wavelength n, so below 2 microns, we see that there's a significant red noise in the data. That's that correlated feature you can see with your eye. So that correlated feature coming from the star gives us about a 200 ppm noise floor on TRAPPIST-1. At the long wavelengths, where you can see that it looks like photon noise, it bends like photon noise, and we don't see that noise floor. If there's any stellar contamination feature, it's below the photon noise floor, which is what we would expect. That's why Natalie's going to get 15 transits. Now, if we divide the transmission spectra, we end up with a relatively flat spectrum for C, but you can see that it's not perfectly flat. In particular, short of 2 microns, we still see some structure in the data. And when we bin that short wavelength data, our noise floor has shifted down, but we still see the red noise there. Our noise floor is now about 80 parts per million. So we've reduced the stellar contamination signal by a factor of 2.5. Which is good news. It's not perfect, but a 2.5 reduction is pretty good. At the long wavelengths, we're still seeing it bend with photon noise, but we can argue that whatever noise stellar contamination signal was buried in that photon noise has also been reduced by a factor of 2.5. It's good news because that's the wavelengths where we're going to be looking for molecular features from TRAPPIST-1e. We can also model the outer transit spectrum. I told you not to do this. I did it anyway. And what we see, even though our models aren't doing a very good job of fitting the data, we argue that we see roughly a coverage of 2 distinct spectral components on TRAPPIST-1 spectrum in this data set. A cooler component, which is about 2,000 Kelvin, a warmer component, that's 2,600 Kelvin, and we think the covering fraction is changing over time as the star is rotating through the observation. The final thing we can do with this data set is we can ask, if it is comprised of these 2 distinct components, where are they located on the star? If the cool component were some monolithic unocculted spot that was covering roughly 50% of the star, as is shown in this example here, the transit light source signature would be stronger than what we actually see in the data. So if we want to reconcile the inferences from the stellar spectrum and the relatively muted transit light source signature, we can play this game where we say the star is a mixture of all these spots, and there's a relative overdensity of the spots outside of the transit cord, satisfying those two criteria, and we get this signal here. So we think that maybe we're not even seeing the signature of spots. Maybe this is like granulation on the star that has some sort of latitudinal dependence. They're small features and they're everywhere, is what the idea that we're going towards. And I'm going to skip over these points just so I can give one very, very short plug to ongoing efforts that are tackling this issue. We've heard about Reveal. There's also Spotless, led by Ignacy Ribas, who is using state-of-the-art stellar activity models and machine learning to try to disentangle signals in RV and transits. And I'm doing a large legacy archival programs on HST and JWST to look at those stellar spectra and try to infer the spottedness of their stars. NASA is also going to launch a mission dedicated explicitly to this, and Nicole is going to tell us more about that tomorrow. So the things I'd like you to take away is that we're in this model-limited regime where we need improvements in stellar models in order to study the planetary atmospheres better. There are empirical ways we can get around this for now. And lots of people are working on this, so there's efforts underway. And I will just leave you with a parting thought from ChatGPT. Thanks for your attention.
All right, thanks, Ben. Maybe we'll be cosmologists, maybe not. So do we have any questions? And do I have mic runners also? Any mic? Oh, I do have a mic runner. Okay, question from Dan Huber in the front. And if any grad students ask questions, I do have Pandora stickers. So think about it. Go ahead.
Can I get one too? No, I guess not. Dan Huber, Hawaii. I have a question about the out-of-transit spectrum modeling and the model challenges. So there have been some advances on this using Apogee, for example, where people have actually successfully modeled star spot filling fractions, including cool stars. So I wonder, the question is it just a matter of resolution? Presumably not, because the higher resolution spectra from the ground. And the second question is there any value of actually getting simultaneous ground-based higher resolution spectra with the JWST data that might help?
Yeah, I think we get complementary information from high resolution, and actually Annabella Meach is going to tell us more about that very shortly. With respect to the Apogee fits, I'm not familiar if they're looking at the whole SED or not, but basically what we're seeing with HST and JWST is we can get a model that roughly matches the distribution of the star, but when we look at the precisions we get, like because the signal to noise is so extremely high for HST and JWST, as you saw in that plot from Sarah Moran, when you really dig down and look at the data versus the model, that's where you see that, oh, actually, the model is not satisfying these data. We need to inflate the uncertainties on our data to get a good chi-square. So it might just be a precision thing with space-based versus ground-based, or I'm unfamiliar with some really exciting recent work.
Okay, any other questions? We have time. Oh, right in front, or from online?
Yes, I'm online. How viable do you think the double planet transit technique could be for two planets that possibly both have atmospheres? Could the assumption that the contamination is broadly consistent in both still be used to break some degeneracies and retrieve stellar / activity parameters to help to constrain correct / unbiased planet properties?
So I think if you have two planets with atmospheres, you do get an extra benefit by looking at both of them at the same time, because you can say that contamination signal is going to be consistent. But then on the planetary side, what you ultimately constrain is like a combination of the two planets' atmospheres. You're always like going to be defining them relative to each other, and so you get better constraints on the joint atmosphere of the two planets than the individual atmosphere. And if you're interested in how this works out, you can look at Julian DeWitt's 2016 paper where he did this for some early observations of TRAPPIST-1.
Okay, yep, one more quick question.
Thanks, great review. I thought Dan Huber was going to say this, so I'll say it. So granulation is stronger at the shorter wavelengths. In fact, Srinivas, who's a PhD student sitting behind me, has a paper on arXiv this week confirming that for red giants with Kepler and TESS. So the fact that you see a stronger signal at the shorter wavelengths is completely consistent with that.
Okay. All right. Well, let's chat some more about that.
Awesome. And so with that, I think we'll thank Ben again.